Yes.
Good. I'm sorry I put everything under announcements. I'm just not I don't know. I guess I need to be more organized in how I do things in Canvas. So while I'm doing this, maybe I could ask you guys, where were we last time? What were we talking about? Let me just grab my notes. Can you think about where we were?
The last thing I have written down is the sample space for tossing a pair of dice.
Good. Very good. Thank you for saying that. So can I ask you a question about that? What was the point of that? What type of sample space was it? It was an example of a particular type of sample space. What was that? What was the? You look at all these outcomes, right? What happened to the first die and the second die?
I believe I just have written here that the cardinality was 36.
That's true. But okay, what I'm doing right now is trying to clue you into that test problem on there. What do we know about all those outcomes? What do we know about? Like snake eyes and boxcars. You guys know what snake eyes is, right?
Mm-hmm.
What about boxcars?
Mm.
That's a pair of sixes.
Oh.
Okay, so what do we know about those outcomes? How many are there? 36, right? So what do we know? Okay, you got the sample space. Okay, I don't want to write them all, but what did it look like? Well, there's an echo in there. I've never heard that happen. Do you guys notice that there's an echo in the audio? It's weird.
Is that me? Wait. Yeah, say something.
Yes. Go ahead.
Is it still echoing?
It is? Is it echoing?
I don't know. No, I was asking you. I was wondering if it was my system.
It's weird because I've seen other things happen, but I never heard, it's like I feel I'm at the Echo Cliffs, in the Santa Monica Mountains. Echo. Okay. Let's just do the 6x6 one, okay? What is the thing? This is a sample space, right? It should be a 6x6. It doesn't look like it is that yet. Anyhow, so what is this one down here? What would be that entry? What is that?
6-6.
6-6. That's boxcars. Does somebody? Is there like another conversation? Do we cross wires with somebody?
I think everyone just needs to mute themselves.
It's okay. Well, as long as they're not talking about anything that they're not shouldn't be. Okay. Okay. What about this? What's this called? This one here. Snake eyes. Okay. So what is the override? Why does this example show up? This is a particular kind of a sample space. So what was the experiment that was done here? You rolled 2 dice, but they were distinct dies. Okay, distinct. Like me, I'm a distinct die. No, but they have you got die 1 and die 2. So this is the result of die 1, result of die 2. All of these guys here, what is? These are outcomes. These are outcomes. What do we know about the outcomes? Is it more likely to get boxcars than to get snake eyes?
No, it's they're all equally likely.
Exactly. What's the chance of getting this one right here? 1 over 36. This is an example of an equally likely sample space. Equally likely. That's very useful because why is that useful to have it equally likely? Well, suppose you were looking at this event. Event, by the way, is a subset of the sample space. So what's an event? This is an example of an event. You might say, if they mean subset, why didn't they say subset? Why do they have to say event? I don't know. That's just the lingo of the subject. I'm just the teacher here. I'm not making up this stuff. I didn't discover any of this. Ethan, oh, you did. Somebody did some tracking down. Okay. So how would I figure out the probability of landing in that event, in this subset right here? Well, because they're equally likely, how many outcomes are in there? How many outcomes?
Is it just 5/36?
Right, there's 5, exactly. And I like the way you said that. It's just. When you have an equally likely sample space, it makes things a lot easier in trying to figure out probability. Now, a person could argue, what I've written here, this is incorrect. And I just want to see if you guys understand about the visualization of this. They could say, you just did it wrong, Don. How could that be wrong? It's not 5/36. Yeah, trick question, right? Look at what I've written. What have I written here? I think outside the box, you guys. I mean, imagine. How could that be wrong? I didn't specify what the event was, right? The way it's drawn, it looks like it's this or this. This is this is the set. The set doesn't have to be contiguous in any kind of way. So if it was everything, what would the answer be? Everything you see, this outcome plus these 5 outcomes. How many outcomes? Okay, so it's possible, right? I mean, the way it's drawn sure looks that way. Are we good? Are we good to go? Are we good? Okay, you're awfully quiet today. What happened? Have a wild Super Bowl party? How is it 6/36? The way it's drawn, it sure looks like this is one event. This and this. It don't have to be just one. It doesn't have to be a continuous, right? I mean, there's no reason. I mean, the way it looks like, I'm including this outcome and these 5 outcomes. That's my event. So A could be what? If we specify it, we have to draw it carefully. So A is what? It could have. It looks. This is an interpretation of what was drawn. It could be what? What is that? 3. 3 comma what? 4. And then what's this guy right down here? 6 comma 2. What else? 6 comma 3. 6 comma 4. And these 2 guys, 5 comma 3 and 5 comma 4. And this is, just the way it was drawn kind of just stood out, That's if you just saw this, you would say my event is these outcomes and this outcome right here. Okay. You have to look at the context, of these pictures, but don't think that all the events or you can put a fence around all your events here. All right? Okay. What next? Let's put down the axioms of probability. Okay. Every math field, every area has axioms. Math itself has these set theory axioms, but here there's 3 axioms that a probability must satisfy. Probability is a set function. It's defined on sets and gives you a number. So this is that set function. So what do we know? So for each EA, I want you to get used to my shorthand. So for each event A, contained in the sample space, what do we have here? We have that 0 is less than or equal to P of A is less than or equal to 1. Okay, and P of the whole sample space is 1. But what else do we have down here? you have the probability of E1 union E2 union En will be the sum of the individual probabilities if what? What condition do I need on the sets? If you've been reading chapter 2, these sets, the probability of the union of those sets is the sum of the individual probabilities if what?
If they're disjoint?
Yes. If EIs are mutually disjoint, any two of them. And you understand what it how do you understand what a disjoint pair of sets is, right? There's a Venn diagram. Venn diagrams are useful for visualizing the relationships between sets. And your typical Venn diagram looks something like this, right? This is set A, this is set B. You should draw the universal set that contains it. And in the case of disjoint, what's it going to look like? It's like eyes here, okay? So these two sets don't intersect at all, okay? If they do intersect, what's the symbolism for this?
Intersects?
Right, but what's symbol? How do we draw that? How do we write that? What's the notation for that?
I mean, it's called a cap, I think. Like cap and cup.
Well, it's the intersection, right? A and B. Yeah. What's the notation? I see. Yeah, right. But good, you have it right, cap and cup. But in our book, in Ross, they dispense with the unhappy face or the cap, and they just write AB. And this, you might say that's awfully confusing, but it makes a lot of ugly things look extremely elegant formulas if you just use AB for the intersection. So the union would be like down here. So this is the happy face. We don't change that, but the intersection we do. Having said that, what is a key proposition? A key proposition. I'm sorry, my handwriting here is not going to be great. Key proposition is that the probability of A union B equals what? Probability of A plus probability of B minus the probability of AB. This is critical for us to do problems involving probability, okay? Just take a look at that. We're supposed to all have this, but it behooves us to look at it again. Look at the way this is written. So the probability of A union B, what we have here, if you read this again. If you read this again, in the red thing there, it makes you think that the probability of A union B is just a sum. But you see, there's no side condition that these A and B, that their intersection is empty. If their intersection was empty, I could just appeal to this third axiom of probability and say that it's P of A plus P of B. I mean, that's it. But that's not what I see above. You see, if A and B are disjoint, what is the probability of A and B? Well, there's nothing in between, so the probability of the empty set is 0. Should have put that. So, now that should be clear. The probability of the empty set is 0. So, it would be the case if A and B were disjoint that this formula still works, but you don't get this other term because it's 0. But how do we in general, they're not disjoint. They have a picture like this. How do we get this? We prove this from what we have here. Well, this is a case where maybe I could be doing this the wrong way, but maybe we put some colors here. We can manufacture some disjoint sets here. So what? What is our situation now? Well, the probability of A union B, it's how can I write that as how can I write it in such a way that it appeals that I can utilize this axiom of probability for this? Well, maybe we have to write something, maybe we don't. So if you look at the probability of A union B, it would be this plus this plus this. But if you just take all of this plus all of this, you're going to count the middle twice. And that's why we have to uncount it one time. You see, because by this third axiom, this union probability is this plus this plus this. But this has only been counting once. But if you take all of this and you add all of this intersection will be counted twice, and it has to be. We have to remove it once. Does anybody know that from maybe Math 320 or 326? What's the generalization of this called? This process? There's a name for this.
This is the inclusion-exclusion principle, I think.
Very good. Exactly. So this is a simple case of mistaken identity. No. The inclusion-exclusion. And this is how I write it. Inclusion, exclusion. Principle. We'll get to that later, but hopefully today we'll use that. And it allows you, it's one of the most powerful tools in counting that I've seen. I mean, besides, of course, generating functions or something like that, but this is a really powerful tool. And there's some problems that can't be, in my opinion, in my belief, that can't be done any other way but by using this principle. Okay, so let's do some of the examples in the book in this section. Okay, I'm going to have to erase something here, but just don't forget this idea. It's very critical. And then when you have three sets, maybe I should just show you that it can generalize this. It generalizes to three. Some people look at this and it's too obvious. Well, it's not. It becomes a little less obvious when you have three sets. Okay, this is set A, B, and C. For some math majors, they know this is a Venn diagram, but they sometimes don't know that this diagram with circles doesn't work if you have four sets. If CS majors know that because they have perhaps more exposure to this kind of thing. But anyhow, it tops out. This drawing method of drawing all the possible intersections tops out at three circles. So in this case, if you were looking at the probability of A union B union C, what's the issue here? There's going to be lots of overcounting, okay? Because if you take these three things, how many times did you count this center guy right here? 3 times, right? So you have to, and this guy here got counted twice. This got counted twice. This got counted twice. So whatever the formula is, you've got to. You don't want to overcount. You don't want to undercount. I probably should tell you what the formula is. You start out with. You start out with what? Okay, so probability of A, union B, union C is going to be what? You start out with the individual ones, and then what do? You subtract off by all of the pairs. How many pairs do I have? I got 3 things. I don't need pairs, so I don't have any. No. How many PAIRS do we got here? You have 3 things. How many ways can you choose 2?
3.
Very good. Plus P of CB. Okay, this is the formula, okay? And then you're gonna, and then what? plus. Okay, so I'll leave it up to you to try to believe that that's true. But you just look at this. I want you to have some intuition here. This center guy got counted 3 times, but also in these loons. These are called loons. These. Okay, let me draw a picture. Each of these guys is a loon, intersection of 2 circles. These guys here got counted in each loon, but there are 3 of them. So that means that now, after subtracting off that, you've got nothing in there. So that's why this last term has to catch this. Okay. Okay, so now we're going to do basic probability with equally likely sample space. But again, to be intellectually honest, there's nothing simple here. There are hidden assumptions made when you make these calculations. We have to be very careful that we don't poo-poo this and say, "Oh, okay, I know how to do it. I can do it." And then the problem on the test, then you can't do it because you didn't have something exactly like that. You guys, have you looked at it? We have, let's see, we got really good attendance. I appreciate that. I really do. Let me tell you why. The test, of course, is take home. So a person could come to the conclusion, I don't need to attend because I have the problems in my hand, I can check it. Don't check it until you're absolutely desperate. I'd rather you not, but definitely don't check it before everybody else has had a chance to try to work it out on their own. It just kills it if, especially if the check answer is wrong. It's just awful. It somehow infects other groups and they get the same thing because the word is out. Well, I got it on a check. That gives you like 0% confidence it's correct. You're going to be very skeptical. And I'm very happy that you're attending the class because this test you have, the midterm 1, is not the only shot you'll get at with this stuff. There'll be a final too, right? So we'll go over it again. So I'm really happy people are coming because hopefully they'll get some experience doing these and not just get some retention on the material. Okay.
Professor, before you erase it, I'm just confused. So this example is the probability of getting the intersection, all the intersection points, what exactly is the?
Either A happened, B happened, or C happened. Those are ORs.
Oh, okay.
You see something like this, a happy face. This is a probability that something in A happened or something in B happened. Now they could intersect. Okay. Okay, so remember, think of these as subsets of the sample space. So go back to that. If you need to, go back to that 6x6 grid of the outcomes of tossing 2 dice. You could ask yourself, A could be that the first die landed even, and B could be that the sum is less than 6 or something like that. So there's definitely an overlap. They're not just joined. Do as many of these as you need. On the test, there is a problem that's involved with this and the die tossing. Okay. I'm moving a little fast because I'm under the assumption that maybe you read through or skimmed through chapter 2 already. But if you didn't, make sure you put some time into that, reading the exposition there. My purpose as a teacher is to just warn you about the shoals, the harder things. Okay, so if you're lost now, think about this. These sets are events. They're subsets of the sample space. Whatever the experiment is, it has these outcomes. Okay, and right now we're assuming that the individual outcomes are equally likely. So all you have to do is compute a proportion. Which outcomes correspond to that event or that condition over all possible outcomes. So it's a mechanical kind of thing to do, but that's where everybody starts. Okay, let me get concrete here and not be evasive. So let's look at example 5b. And what's the story with this? You're going to get used to the word earn in this class. If you earn your grade. No, there's a different kind of earn. urns are like usually have balls in them, and they're all mixed around, and you take a random sample out of it. So in this case, there's 6 white balls and 5 black balls, and you want to draw 3. And whenever they do a draw, it's considered random. Okay, there's no looking and figuring out which one you want. No, you just randomly choose 3 out of here, and they want to know what's the probability of getting your check here. 1 white one and 2 of the black ones. Now, I know some people in the class know how to do this. I'm not looking so much for the answer. I want us, being a third-year class, I want you to think a little deeper about the assumptions. What are the assumptions? This is not easy, okay? What are the assumptions here? Okay, well, in order to figure out this probability, we'd have to know the sample space. So it really depends on how you regard the sample space. This is something worth taking some time to become comfortable with, because you could think of the sample space as all unordered sets, subsets of 3 of these. So in other words, you think you have 6 white and they're distinct, and the 5 black are distinct, but unordered, the order doesn't matter, just what are they? So the sample space then would have, if they're unordered white and black balls, so how many, you're doing 3, so how many ways could we select 3 from these 11 balls here? How many ways could we do that? How many ways could we select 3? Well, how many are there to choose from?
11.
There's 11. Somebody said the sample space is 11 because if you reach in, you can grab it. Exactly. How many different ways can you grab unordered? You know, like not the first one, the second. Just how many ways can you grab it? Well, there's 11 balls, and so these are distinct, right? There's 11 balls, and you can choose 3 of them in that many ways. Okay. But then on the numerator, we're saying we want to make sure that we have 1 white one and 2 black ones. So the white ones, you have to think about this, that there's 6 of them, right? And they're distinct. So how many ways can I grab one of these white ones here? Well, there's 6 possibilities, right? So 6 choose 1. Now, so you've got your white ball. How many ways can you choose 2 black ones? So how many black ones are available? Let's see if I'm in the. So there's 5, right?
5 choose 2.
Right. So there's 5 of them. So we're going to choose 5. I want you to realize the importance of the fact that these balls are, the way we set this up is they're actually distinct. Okay. And again, but not only that, but we don't care about the order in which they were chosen. So there were 5 to take, and 5 to take from, and we want to take 2 from that. So you might say, well, how is this equally likely? Well, all of these ways of grabbing 3, assuming they're distinct, they're all equally likely here. Okay, think of it as grabbing 3 here. Okay, you don't care which one's grabbed first, and the second one, and the third one. We don't think that way. This is the best way to view this. Let me check the chat real quick. Yes, 11 choose 3, correct. Somebody already knows the answer. I don't know what the answer is. I don't know. What's the top here? 6 times 5 choose 2. 10? It's 5 times 20. I think it's 10, so there's 60 on top. What's on the bottom here? What's 11 choose 3? Over 6. So 3 goes in there 2 times. 3. No, 3. Okay, 3 goes in there 3 times. There's a 2, so 5. So what's 15 times 11? It's 165, right. So this is, I'm getting 165. I don't know, what's this supposed to be here? How many 15s are in 60? 4. How many 15s? 1, 11. Okay, so it looks like the answer is 4 over 11. But again, my purpose is not just to spit this out and have you memorize it. I want you to really believe that the sample space is equally likely. It doesn't matter which 3 you grab, okay? You know, it's all equally likely. You've got 11 balls, and any 3 could be what you could be the outcome of this random selection. And then you might say, why are these multiplied instead of added or something like that? Well, you know, we're looking at different possibilities because look at it this way. You're going to choose one of these white ones, right? So you chose this one. And then here you're going to choose 2 of the black ones. If you had chosen a different white one, like W2, that would have been a different selection. So, you know, even though this was the same, so you've got to multiply here. Okay, you've got to multiply. Okay, does that make any sense? I mean, but I'd still say this, if you want to, if you're a math major, for sure. I don't know how many math majors I have in this class. Probably not that many. If you're a math major, you could set this whole thing up with permutations instead, and you might feel more comfortable with that, and then prove that you get the same answer. But if you're a computer science, you're probably more answer-oriented, not so concerned about the underlying, proving things. So to me, this is a more natural way of looking at it. Okay, so let's go to the next example. Again, what am I doing here? I'm trying to get through chapter 2 so you guys will be prepared to do some of the problems on the test, some of the stuff we haven't covered. Has everybody looked at the test so far?
Yes, quick look.
Yeah, so there are some things that are, well, first of all, I try to be creative. I try, I'm just human. I probably made mistakes about that in the sense that maybe somebody, when I was at some other point in my life, I encountered that same problem, and now I think it's my own, and not knowing that in my mind, I'm just recollecting. But I don't recall seeing any of these problems. So it's, again, why am I doing that? Well, of course, to escape the Chegg monster or the Slater monster or the math stack exchange monster, whatever, because I don't want to make this into a game, the tests. I want to give you something of quality. And also, it's more satisfying to me to try to find a new problem. Okay, let's look at the next one. Let's look at what's the next example? The next example is not that easy, so you have to pay attention. It's a step up. And what's the example number for this? Now you know why we don't have notes in this class, right? We go off the book. Example 5F. Example 5F. Okay, now this is a problem that deals with cards, decks of cards. And there's so many problems involving cards that if you never played cards, or especially you haven't played for money, if you play cards for money, then you know exactly the composition of a full deck. And you always want to be dealing from a full deck. I mean, you should know no jokers. There's no jokers in there. And a full deck has how many cards? So a full deck of cards. So we're dealing from a full deck. So how many cards does it have?
It's 52.
Yeah, there's a song, right? There's some stupid song from the 50s or 60s. I'm really old. Whatever. It had to do with the deck. So it's divided. I hope nobody knows that song because it's so stupid. Once it infects your mind, you can't get it out. I forget what group that was. If somebody knows that trivia, please butt in. So it's divided into these 3 so-called suits. And these are, we already talked about the difference between, queens of diamond and queen of hearts. You got all that stuff. What are they? So the spades, clubs, and diamonds, spades, queens, and of course, close to my heart. But so these are the suits, but the actual face value of the card goes like what? It goes, what does it start at? So you have aces, twos, threes, fours, 5, 6, 7, 8, 9, and 10. And remember that these could be any suit, but the thing is, how many do we have to have in order to come up with 52? So you have to a full complement has to have what? Jack, Queen, and King. So it better be 13. If it's not, how do we know it's 13? Yeah, it's 13. Just count them. This is like a 1, 2, 3, 4, up to 13. So this problem, and it's not that easy, it asks you for the probability of getting dealt a straight. Okay, again, this is not this, but this is the way we got to get used to this in Ross because he doesn't pull any punches. Yeah, it's not going to be easy, right? So, if you were taking a test and had to do this and was seeking partial credit, just get the denominator first, okay? Because that's the size of the sample space. And what is it? What are the equally likely outcomes of being dealt? You're dealt 5 cards from this. So how many cards total? How many cards total?
52.
52. Okay, and of the 52, when you're dealt a hand, why do they call it a hand? Let me pick on somebody out there. Everybody's heartbeat is going up. I'll never pick on somebody who has their video on because I think that's okay. Why do they call it a hand?
5 cards? 5 fingers?
Yeah. Okay, so 5 cards, 1 per finger. So these are all the possible hands here. But then all we got to do is count the number of hands that result in a straight. So what is it that qualifies something to be a straight? This is a little complicated. A straight means that if you put them in order, there's no gaps. Like if you go 3, 5, 6, 7, 8, there's a gap between the 3 and the 5. So how do we do this without a gap? If you put them in order and you end up with 3, 4, 5, 6, 7, that's an example of a straight. And it doesn't matter what suit these are. Okay, when it's suited, you call that a flush. But in this case, it's just it's a straight. This is probably irritating to some people that don't know anything about cards, or they're irritated by their significant other playing poker and losing money or whatever. But I mean, it's just, if you don't believe me, look at how many examples involve cards. It's just part and parcel to this subject that the examples go this way. You have to get familiar with what with what's in the deck. So the thing we should ask ourselves is how many straights are there? Because then we'll know. So how many straights? Well, let's see. I've got 1 right here.
So
It's 9 straights,
I'm
right?
really sorry.
Yeah, go ahead. It's okay.
I had to go do something real quick. How did we get 52? Choose 5.
Okay. 52 is the number of cards in the deck. And we're going to we want to know how many hands of 5 are possible.
Okay.
This is a large.
So why are we? Oh, I get it. That's why we're dividing. That's the sample space, basically.
Yes, right. And also it helps. Again, you probably think I'm crazy for those little details, but do you hear that? Somebody needs to. What's happening is that the audio is going back and forth.
Yeah, that's me.
Okay. We should know how big this is. Is that number in the thousands, in the 10,000s, in the 100,000s, in the millions, in the tens of millions. We should know to get some idea when we get an answer whether it's reasonable or not. Can somebody tell me how big that is? 52 choose 5. Let's put it somewhere. This is something you should have available, so you know if your answer is feasible. Excuse me. It's feasible or not. How big is that number? 52. Is it like 2.5 million, or is it what is it? How do you use it on the calculator? I should have, for a class like this, I use one, a graphing calculator, because when I'm doing a problem, I've got to get the number. I want to see if I get the right answer. So you got to have access to a calculator that does this calculations. This is NCR on my TI-89. TI is NCR 52,5. What is that? How big is that?
If my math was right, it's about 2.59 million.
So about 2. You say about 2.
So
Around there.
About 2.6 million. So that's if I canceled things out correctly.
Well, this is. I'm not kidding about using the calculator.
I didn't use the.
Yeah, I'm not kidding. For this class, especially for this textbook, he loves to do examples where there's a calculation or several calculations involved. So let me just double check.
I'm using a calculator, but I didn't remember how to do factorial, so I just I can't. I don't know if I'm doing it right, but I canceled some things out and then multiplied
I'll
with
check
the calculator.
It's just, it's not instantaneous, but I'm telling you, this class will be a meanie if you be so much harder if you don't have this. You can pick up a used one somewhere. I wouldn't say this, unless it was really okay. He's right. It's 2,598,960. That's a lot of different hands. Okay, so that's the combinatorics it's astounding. So that the chance of getting the same hand twice in an evening playing poker is pretty low, really low. Okay, so
that's counting the number of different orders in which you got the hand, though, right? So
no, that's be careful now. This is just.
No, it's not.
Order is not important.
Oh shit! Yeah.
You count the orders. You see, sometimes maybe you're a gambler, because in Vegas sometimes the way it was the way the cards came out, you can get different side prizes or something like that. But it just like getting a royal flush in order as it's doled out. That's impossible. It's just not going to happen. Don't fall for that. Don't fall.
I guess it's the probability is even worse though, because I think they use like 3 decks sometimes, and when they.
Well, I was speaking of poker hands, but it's okay. But it's but let's ask ourselves, how many straights do we have? Those are cards that when they're sorted, they don't have any gaps in between them. Okay, so let's just look at this. So this is your 13th card, right? And this is your first card. So how many straights are possible? Well, it's what is it? I mean.
Well, can you wrap around? Like I don't play poker, so would Jack, Queen, King, Ace 2? Is it okay?
Yes.
Okay.
You can. Let's do. Yes. Let's. I was gonna not tell you and see if something came out wrong, but yeah. So you can. Let's just consider the ordered list here of these. Yeah, you can wrap around.
So there's
wrap around
10 possible per suit, correct? And you're choosing 5 cards from each suit. So there's 4 suits. So it's 10 times 4 to the 5th.
Well, I just want to get the number of. Let's do this. You're right, but let's do this in a orderly fashion. I just want to get the number of straights right now. So, okay. So how many are there? So let me go to a different color. So you take 5 at a time, right? So there's 1. And what's the last one you can take?
King through 4 or 3. Well, if you can wrap around, right, it could be king through.
Well, no. I did the wrap around here.
Oh, okay.
Okay, so this is interesting. This is like we haven't even, we're just getting started, and it's like a difficulty that we're facing right away. So definitely, I just have to count how many of these windows you have up to here. So it looks like you had one starting at 1, and the last one was starting at 10. So I'm associating, equating 1 with ace.
Okay, but so Jack, Queen, King, Ace 2 would not count.
Sure, but no.
Would it count or no?
No,
Like that's
no.
just my question.
Oh, sorry about that. I sorry. It's no, the ace is like a dual character.
Okay, it can be Ace can be first or last, but
Yeah,
it
right,
can't
I'm sorry
go
about
around
that.
to 2. Okay.
No, it's not a complete wraparound. So that's why
Got
this
it.
counts all the cases. Okay. So again, how many of these green brackets are there?
So in that case, there'd only be 10, right?
There's 10. So there are 10 base, 10 possibilities. However, it's irrespective of the suit, okay? So how many possibilities are there for the suit? So each of these has what?
You're picking 5 cards out of the 4 suits, right?
Well,
For one hand.
well, I want an ace, a 2, a 3, a 4, and a 5. So how many ways could this occur? Because each one, ace appears in 4 different suits. So there's how many possibilities for this?
4 to the 5th.
That's right. So there's 4 possibilities for each one of these, and they're all different, right? So that's, if you multiply these guys, I don't know if you can see the green marker, each of those is supposed to be a 4. So that's 4 to the 5th. So each one of these straights, numerical straights, is realized in 4 to the 5th ways in selections from the full deck. But this is the thing. This is what makes Ross, tricky kind of guy, because that's not the answer. Somebody said, does 2.59 million number mean the number of? Yes. That's a lot. It's a lot of hands. Now you know that why these card games are not simple. The combinatorics are astounding. Never is boring, Okay, that gives me that, but something has to be adjusted. I can't just do this for the answer. That would be incorrect, even though the answer would come out to be close to what's in the book. And this is just a knowledge of cards.
Because like if we call it like a straight flush, we wouldn't call that a straight.
Yes, exactly.
Okay, that's the reason.
It's very anti-intuitive with the language, because usually if you think that a straight flush is a kind of straight, right? It should be. No, they count that differently. If you got a straight, that's not the same as getting a straight flush. Straight flush is what? A flush means they're all in the same suit. So we need to adjust this here. We've overcounted currently, and I need to do what? I need to subtract off those cases where it's a flush. So how many flushes, how many different flushes?
10 times 4, right?
Well, I'm keeping the bracket, you're right. So.
No, I mean, like, that's the number of flushes, right?
Yes. But I mean, right. But in this case, I mean, they all of these being in the same suit. So there's only 4 suits. So I only have to subtract off 4 there. Take this one right here. Right?
Oh, I see. Okay, gotcha.
Okay, yeah, you were right. But if you just take this one, these could all be hearts, spades, clubs, or diamonds. There's 4 possibilities. Okay, soak that in. Anybody have any question with that?
So, what does the 4 to the 5th represent again? And I'm just getting kind of slow right now.
It's okay. I'm slow too. So the 4 to the 5th was what? There are 10 selections of numerical selections, okay? right? For the straight, you could have this bracket. You could have this one. What's in between my fingers? Can you see? Or what's in between my fingers here? 3, 4, 5, 6, 7, 8, or 4, 5, 6. 5, 6, 7, 8, 9. Okay. You see that these brackets could be numerous possibilities, like this one here: 10, Jack, Queen, King, Ace. So how many of those?
Right, those are all straights with
Those are 10, there's 10 possibilities. But within each one, like suppose that you'd have an ace, a 2, a 3, a 4, and a 5. There's many ways that could occur, because the ace has 4 choices of suit, the 2 has 4 choices of suit, and so forth. So that's why every one of these can be shown 4 to 5 times. It's a lot. There's only one thing I'm missing here. Notice that I'm missing something from this explanation. What are we missing here? Suppose this was on one of my tests. What do I always like to see? I want to see an answer. So before you say it or you look in the book, the probability of getting a straight is not very high. If you watch Pro Poker After Dark or anything kind of like that, or if you are a poker player, being dealt that is really really low. So when I say low, what do you mean? Is it 10%, 15%, 1%, a tenth of 1%? You know, what is it? What is it? Just take a guess in your head. Just be thinking, what do you think it could be?
I'm thinking about 0.5%. That's my guess.
Okay, say that again.
My guess is 0.5%.
Which is decimal what? 0.0. You're pretty close.
Yeah.
You're pretty close.
That's from experience.
Yeah, you're pretty close. It's 0.0039.
Nice.
Yeah, you get some brownie points for that.
Yeah, it's just because I rarely get them.
Yeah, well, yeah. You know, some people are old enough to gamble, go to Vegas, whatever, and they play video poker, and you know, you get payoffs for getting a straight or something. They don't understand why the payoff is so low compared to how rare it is to get that. Well, somebody had a question.
Yeah. Isn't like Full House like higher than a straight?
Well, let's
but
do
it's
that.
Like less.
Let's
so
do
it's
that.
more likely, isn't it?
Yeah, but let's do that next. But I just want to explain something to people. If you're playing video poker, you get dealt, you know, a hand, but then you can discard some of those and get them replaced by fresh cards. And so your chance of working your way up to a straight, if you weren't dealt one initially, is higher. And that's why it's possible. So some people are under this mistaken notion that you have to be dealt it straight out when you're playing video poker. That's not true. It's -4 because we're removing the flush cases. Exactly. Yes. Very good. Very good. Okay. So I guess this next one is harder. As you can see, I don't think about these, cards. I'm not a card player. But anyhow, so the next one is what? The next one to do.
Wait, before you erase, so I know how you got 10, because I counted each possibility.
Yeah.
But is there just an explanation, like some sort of?
Yes. So
because I just drew out the groups, but is there a way to like divide something to find that number?
No, I draw it this way. We can see it.
It's the number of places that you can put that bracket once you put them all in order.
I think
but is there like an equation instead of drawing out each bracket? Is that whatever? No, you just have to draw it out.
Yeah, but I'm not really drawing out. This is an elegant thing because I'm asking how many brackets there are, and just stay with me here. If you look at this, the last bracket starts at 10, right? Right? I mean, the last one, right?
Okay, yeah.
But what does the first one start at?
1.
So how many brackets are there?
In between?
Well, total. Just if I count this one all the way up to the last one starts at 10. The first one starts at 1, the first bracket.
Okay, I think I see. Yeah, if you count from 1 to 10.
Yeah, that would be
Okay.
10, right.
Yeah.
Right. I mean, it's not obvious because we had to start at an ace, right? But you want to think of the ace as being like a 1 here. And then, so if you write it down, to me, this is the elegant way. You definitely don't want to use a formula in this case. You want to, pictures are worth 10 to the 3 words, right? I think this picture is very helpful.
Yeah, I believe if you wanted an equation, I mean, but based on that explanation, like you see where the bracket ends.
Yeah.
It's always going to be like the length of the bracket has something to do with it. So you have the length of the list, and then you just subtract the length of the bracket from that and add 1.
Okay, look.
So it's like
Okay.
that's how many different things that you have because it's counting.
I'd be, not teaching well if I didn't. Okay, let me just give you something that you'll need. If not now, if you're CS, you'll need it at some point. Let me write some consecutive numbers, okay? Okay, right? In this list. What is the form? This is something that is important to know. How many numbers are in that list? What's the formula? Well, you look at the index 3, 4, 5, 6, there could be the index, right? So these are the indices. So you take 9 minus 3 plus 1. What do you get? 7. Are there 7? 1, 2, 3, 4, 5, 6, 7. You go by the index. You always have to add the 1. So you might say, well, what is that? Well, no, we use that constantly when you're proving things in computer science. Constantly.
Yeah, it's a funny thing about indexing versus counting. I had someone I worked with at Five Guys when I used to work at Five Guys drove me insane every time June came along because she would say, "Oh, it's the 6th month. We're halfway through the year at the beginning of June," and I'm like, "No, we're not. We're 1 month away from halfway through the year."
Well, if there's 13 months, you have a middle month, whatever. Yeah.
But there's 12. So if it starts at 1, then the middle is actually at the beginning of 7 or the end of 7.
Well, but the middle is, okay, so. I'm an expert on middle, believe it or not. So, okay, if you got 12 numbers, what is the median? Basically, you're asking me. And it depends. You could return the lower median, the 6, the upper median, 7, or you could take the average, 6.5, which would occur June. Okay, that's 15th, right? So halfway through June 15th, whatever that is the middle. But this is a problem. This is a problem. People don't understand when in computer science, you don't take, in the even case, you don't take the 2 middle numbers and average them. You take the lower median usually. Okay. So that's something. If you're CS,
that's true.
You get 1. Okay, so what's the next part?
When it deals with, for me, I think of it also in chunks of like, what do you call it? Maybe more calculus terms. So like an amount, like a specific amount rather than a single number. So it's like, I don't know. Sorry.
That's okay. It's okay. But in discrete math, things are granular. So, there's very little calculus in at least what I'm doing. So, but anyhow,
yeah.
What's the next problem? Example 5G. Example 5G. So now it comes to the one you were mentioning, a full house. Much different than this, whatever the proverbial red brick house. It's just a full house. What does that mean as a hand, as a poker hand? I got to remember that. So I think it means you have 3 of a kind.
Yeah, 3 of a kind plus 2 of a kind.
And a pair. So
I like to call it 2 of a kind.
So if you have that, so what are the kinds here? Do they mean suits? No, they're saying like, what would be an example of this? They're not referring to suits. Here's an example. You could have a couple 2s, and then you could have like 3 jacks. That would constitute a full house. So, whatever, the thing is, with this kind of problem, you can get partial credit by, the easiest thing is to get that denominator because we're assuming equal likely sample space. So how many hands are possible? Let's go over just as a review. It's 52, choose 1. And how many? It's about 2.6 million, which is coincidentally the median home price in my zip code in Santa Monica. I found out this morning. My place is 400 square feet, so it's way below the median. But I'll never be able to move up to a real house, you know. Kind of like Pinocchio, right? It's whatever. Okay, so how many ways could we? How many kinds are there again? So we could. I had written it down before. You go ace up to king. So how many is that? There should be 13 kinds, right? So there's 13 kinds, and how many do I want to? I want to take up. Okay, I got to think about this for a second. I need to select the two kinds I'm going to use, right? So what would be another example of the two kinds I could use? I could take a pair, say 2 aces, and then I could take 3 threes. So I have to. There's 13 kinds, right? So I need to take how many? I want to select 2 of these kinds. Is everybody good on that? Those are the 2 I'm going to use to build my full house here. So what happens now? So I've got the aces and I've got the threes, but how many ways can I choose for the pair, the aces? How many ways can I choose them? Somebody has it there. I see it, but isn't 3 of a okay? Isn't it 3 of a kind? Did I not? Oh, I'm choosing the 2 kinds right now that I'm gonna. So I'm gonna choose 2s and jacks or aces and threes. I'm just choosing the 2 kinds that that will be in my full house. Is that okay? I'm just getting started.
Yeah. So it would be so there's 4 different kind. There's like 4 different aces, so you could do 4 choose 2 for just that pair.
Right. Well, you seem to have a good familiarity with this. But is everybody else okay? I've got 30. I'm looking at 32 people. I'm just worried. Is everybody okay with the start? Somebody says, "Oh, thanks." The -4. Okay, it's old stuff. So, yes. For instance, for the pair, there's 4 aces, but we need to choose 2 of them. That does the pair. And what about the trip? Well, from the trip, we want to choose 3 of those. But there's something missing here, because this is sort of a subtle point. Okay, think about this now. We've chosen the 2 kinds that we're going to represent in this full house. So we got 2s and jacks, for instance. But it could be that the 2s occur 3 times and the jacks occur twice, as opposed to the 2s appearing 2 times and the jacks 3. Do you understand that? So just because you chose the 2 doesn't mean you covered all the cases, because one of them is going to show up 2 times in the pair and the other one is the trip. So what do I need to multiply this by to get the full count? It's a full house, so we need a full count. It makes sense, right? Yeah. What do I need to multiply by? Uh-oh, I've got utter silence. Maybe we disconnected. Are you guys still there?
Yeah, we're still there.
Thanks, because it's like dead. You know, like, did somebody die? No.
Our brain.
If somebody died, it's most likely me. The probability is higher. I guess I'm still vertical for the moment. You understand why you have to multiply by 2? Because let's put it this way, okay? Let me just make it as clear as I can do it, as humanly possible. You could have 3 2s, right? And 2 jacks. But I've still at this point, I've selected the 2 kinds. But just because you got the 2 kinds doesn't mean you got every case. For every choice of the 2 kinds, there's going to be 2 here, right? Is that good? You guys good with that, or how do you feel about that?
What about the case where you get a 4 of a kind?
No, because okay, you want for a full house, you want to get 3 of one kind and then 2 of the other kind in a pair.
Yeah, but what if you get 4 of a kind of like a 2 or a jack?
Oh, you don't count that because you see, because look at this right here. We're choosing the 2 from that kind for the pair, and the 3.
Oh, okay, I see. I see.
So we actually make that we take that into account.
Okay.
The tricky thing is 2, and some people they don't know why that 2 just suddenly popped up.
It's because the 4 choose 2 can either be the 2 or the jack, and the 7
Yes.
4 choose
Exactly. Wait a second. Hold on. Now, did you say the right thing? Hold on. So you know you've got jacks and 2s here, okay, from this term,
Yeah,
but we don't know which one is the trip.
yeah.
Elizabeth, you okay with that? Uh-oh, good. You're honest. I
No,
appreciate
I'm
it.
not. Yeah, I'm like, I can see the 13 choose 2 because there's 2 possible like choices, 2 types, like the number, 2 numbers or faces. But the 4 choose 2, I'm trying to figure out, is that like because there's 4 suits?
Oh, no,
And
it's
then there's
simpler
2
reason.
cards?
Oh, yeah, there are. Exactly right. There's 4 suits, so there's 4 2s. There's the 2 of diamonds, the 2 of hearts, the 2 of, you know what I mean? There's 4, you're right. There's 4 of them, but we only need 2 of them for this hand. Right, so you have it.
It's like there's 4 individual cards once we've narrowed it down to one kind.
Yes,
And so
exactly.
you just choose
Everything
2
you
of
say
them.
is correct. Yeah, everything you say is correct. Everybody's saying the right thing. So I okay, so I'll just shut up here and listen to you guys for a second.
Yeah, but where's the 2? You're multiplying by 2.
That's the tricky thing, okay? And I got to be honest with you. When I was preparing last night, I left it too late, and I tried to do this problem myself, and I didn't put the 2 in. And I was quite embarrassed when I look at the book. It's a 2. Why does this 2 occur? Because all that's been done.
Does it have to do with the order, or?
So I don't know if I'm in the washout here. But
Yeah, well, order is actually exactly it.
This is the choice of kinds. This is the choice of kinds. Okay, so this tells you which one is a trip. Which one is the trip? That's probably hard to read. But this, you see, it could be just because I chose 2 kinds. I chose 2s and jacks, right? In this case, I got my 2s and jacks, but the 2 only shows twice. Okay, in this scenario, which is also I've chosen 2s and jacks, the 2 shows 3 times. So once you've chosen your 2 kinds, there's 2 different ways that they could be used. Those suits could be used to those choices. Excuse me, those numerical choices, face cards, like you say, to make the full house. There are 2 different ways. I've got 2s and jacks, but it could be the 2 is the pair, or it could be that the jacks are the pair. So there's 2 possibilities there.
Okay, I get it now.
For what it's worth, I mean, whenever I did this problem on my own, I got exactly the same answer, but I wrote it a different way. My thinking was not to do 13 choose 2. The reason being, you use combinations whenever the order doesn't matter. But here my thought was, no, the order matters because it matters if you get the pair or the 3 of a kind.
Right.
So, I mean, I also teach middle school, high school, so I just wrote 13 pick 2, but you could also just write 13 times 12.
Yes, and to be honest, and thank you for that comment. That's excellent. The Ross does it the way you did it. But if you look at his book, he goes 13 times 12. But to me, having done some of these icky problems, like the birthday problem, triplicate problem, I have a definite feeling that I prefer to approach it this way.
I mean, either works. It doesn't really matter. You're either not counting the order and then multiplying the order back in.
Yes,
or,
right. I get it.
Just going about the order.
I get it, but the plants start out the same, right? But when it comes into a tree, they look different. It's like when it gets more complicated, we have to make a decision how we're going to do it. And I prefer to do it, keep it choose as long as possible. even though I had to fix it here. I'm telling you, I didn't.
Yeah, it doesn't really matter. It's fine.
At this point, it doesn't. But
Right.
when the problem gets ickier, I have to be consistent. How I'm going to handle this kind of problem, because you see, if it gets more complicated, then you'll see maybe the pattern will jump out more, because you'll add up the twos will start increasing their exponent in a regular way. Okay, speaking of the triplicate problem, so let's talk about the birthday paradox if we have time. We have all of 2 minutes. Let's go to the next example. In those 2 minutes, I'll give you I'll try to tell you what the next step up here. So let me check the chat, make sure we're clear. Okay, so this problem is infamous. And the problem is, it goes like this. And it's referred to as the birthday paradox. And I wrote right through the glare, so I hope you can read that paradox. Try to give you an explanation why it's considered a paradox. So you want to know how many unrelated people in a room before probability of a collision is greater than 50%. Okay, now I'm using some lingo here that I'm going to be using repeatedly, and you'll learn in computer science courses if you take more of those. What is a collision? So a collision would be two people have the same birthday, the same month and day. Forget about February 29th. Assume that doesn't happen.
Professor, that's a greater than symbol, right?
Yes. Sorry, it looks like a 7, doesn't it? Probability of collision is more than 50%. Okay, do you understand the setting? So these are unrelated people, no twins, no Star Wars stormtroopers or something like that. It's 145. Okay, so just give me a guess. How many do you have to have before it's likely that two people have exactly the same birthday? And then we'll wrap it up. Just give me a guess. How many people? How many people for sure you're going to have a collision?
Well, if you have like 600 people,
well, you don't need
366.
Yeah. I mean, you can get 366.
Yeah, that's right. Pigeonhole. Whoops.
Soon, 365 possible birthdays, and they're all equally likely. How is it possible that birthdays aren't equally likely? You think about that, okay? You think about it. Imagine the scenarios where they're not equally likely. But assume they're all equally likely. Give me a number.
366 possibilities, right?
Okay.
Because of a leap year?
Yeah, we're not counting the leap year.
Okay.
Just assume that didn't happen. So, how many do you think? If you know the answer, don't say it. But how about the lady that teaches middle school and high school math? Did you ever do this?
I've done this.
Oh, okay, good. I was going to say that's something that you probably
I'm thinking 80.
Okay, 80. What else? And then we'll go. Give me some other possibilities. How about 86 or 84? This is an answer to a different question. This is the 84 is the answer to if you're asking the likelihood of a triplicate where 3 people share the same birthday. So that gives you a hint. It's going to be less than 84. Okay, I think I have to go, but I'll hang here to entertain guesses for the next 2 minutes. Thank you.
Can we go over this problem on Thursday?
Yeah, but I don't want to deprive you of being able to take a guess. Just picture it in your head. You've got a room of people, and you want to how many people do you need before it becomes probable that there's a collision between two in birthdays and have the same birthday? If you haven't seen it before, this is really shocking, but what do you think? Huh? Say again?
24?
What makes you say 24?
Double the number of months. So you would have the average-ish 2 people per month, and then you start getting 50% collision. I'm completely guessing.
Well, that would assume a very uniform distribution, right, between the months. I mean, when you have, it's random, right? So when you have 24 people, you wouldn't expect them to be uniformly distributed in months, right? I mean,
True.
I'm not saying it's just the way it is, right? You're taking a sample of size 24, right? Okay. Somebody tell me the answer. They know it. They know it. The 24 was pretty darn close. Okay, for AIM. So you know the answer, right?
I don't remember off the top of my head. I think it's like 21 or 23, something
23
like that.
23 is correct, but since you already have exposure to this idea, maybe I could give you some, enrichment idea that, what about 3? What if it's looking for a triplicate?
I haven't done that one. I could try to tackle that one and show that it's 84.
It's around it. Don't take me exactly. I'm
Okay.
It's so difficult, and I say difficult in kind of an annoying way that people have not been able to find it. I found it on the web the last time I searched, but it took a long time, and apparently that web link is gone. So I don't even know that it's available on the web.
Okay, but are you suggesting that it's a pretty complicated problem to solve?
Not complicated. It just requires a little insight to get started. It's just icky with a lot of, you got to do a lot of cases.
Right.
Problem.
Okay. Well, I can try to tackle it.
Just to the point of setting it up. So you're going to do it by taking a compliment, and you have to be clear on what the compliment is. Mm-hmm. So that's the trick to doing it. But it's a classic. It's a classic.
Yeah.
It's called the triplicate problem.
Mm-hmm.
So do you if I may ask you, do you teach currently in middle school?
Well, yes and no. So it's more, I've done tutoring, and I had a student who was homeschooled, and she had dyslexia. Well, she has dyslexia. Mm-hmm. And so she went up to her school and said, hey, can you, we basically have to get outside tutoring. Can we get covered for this? And so the school, it's to be clear, it's a private school, so they can get away with this. Right. It's just said, well, yeah, we can subsidize that. And they recommended me some other of their students that had learning disabilities. I've taken some outside classes on working with students with learning disabilities. Mm-hmm. So I'm still working on my bachelor's, sure, but I at least have that experience and exposure. So yeah, so I'm kind of working. I do have a school that's paying me, but I'm trying to get my credential and actually become a full teacher right now.
Are you interested in getting a credential in special ed? I mean, because that's pretty.
Well, right now I'm working on the math credential, but and to be fair, my experience so far is working on kids who are still in the normal class. They can still keep up with everyone else. They just need a little extra help. So I am not going, I don't have experience so far in working with students that need to have their own designated special ed class. Mm-hmm. Although I'm not opposed to it. I think that students who are in special ed are very smart in their own ways, and they just need to be taught differently. So, that's something that I'm considering down the line, but right now, just a math degree.
I think I know that in public schools, special ed is it's hard to get those people. There's a lot of demand.
Yes, there is. There absolutely is. It's one of the first things that I was told with taking this. It was just a class. I was at UCLA and they were offering it, and I'm like, sure, I'll take this. Is if you go into special ed, you'll have a job anywhere you go. Because there's just not enough good special ed teachers. So.
Well, I have to give my 2 cents into I might